Well, hello everyone. I am Emin Durmishi. I'm assistant professor at University of Tetova, North Macedonia. Uh, so today we're going to talk about digital topology and board games. This was first meant as a presentation on Portugal that it was organized previously, but I couldn't manage to come to the Portugal. That's why I modified it. I put some additional slides, and here we have the first webinar on our cost action, working group 4. So let's begin. First, I will say some words on my previous research. So I have defended my PhD thesis on 2022, June 2022. Coverings and chain connectedness, continuity over coverings, the title of the thesis. It had to do with a new notion here that we have defined: chain connectedness, continuity over coverings, and proximate approach of intrinsic shape theory. I won't get into these in details. I'm just mentioning if there is someone who has knowledge about these and has any idea how we can implement these in the game tables, would be welcomed. However, so as you can see, I haven't mentioned here digital topology. That means that it's not my main research topic. However, I have some knowledge on digital topology, and I thought we can implement them into the board games. That's why we have this webinar with this title. So let's get into what we're going to talk about, our theme for today. So we will have some introductory notions on digital topology. We will talk about 4 adjacency and 8 adjacency, about Kalimsky topology. We will also introduce some other adjacencies, and in the end, we will have some insights on possible application to all of these into the board games. So let's begin. Some historical notation, facts, we can say, notations. The digital topology was first introduced in 1970s by Rosenfeld as a tool for studying topological properties in image processing. And I can say that till now, digital topology has been applied mostly on image processing. I haven't seen any application, for example, to board games, and I think this would be something new if it happens to have some results. We will see. After this, there have been several papers till 1990 where Kalimsky and some other co-authors introduced, in fact, Kalimsky have introduced the Kalimsky topology before, but on this particular year, he published a paper where he used the Kalimsky topology as a consistent tool in digital topology. We will see further why this Kalimsky topology is very important here. And now let's begin with introducing the notion of digital space. So by digital space, we mean a pair, set of points, let's say phi, and a relation, a binary relation into that set, V, which has the properties, it should be symmetric and irreflexive. And for any 2 points of that set, we will call that they are adjacent if they are in pi relation with each other. From now on, instead of B, we may take the Z square, and we will not emphasize the relation, the agency relation. Instead of Z squared pi as an ordered pair, we will only write Z squared. We introduce here some adjacencies that can be defined in Z squared. So let P be some point into the Z squared set, which we will later call digital plane. It would be better if we see the pictures and then explain, or maybe it could be pretty well explained only looking at the pictures. So by for adjacency, for a point, we mean a point up of the point P, below that point, to the right and to the left of that point. The 8 adjacency, except these points, you also take the diagonal. So in Z square, you can define two different relations, the relation 4 adjacency and 8 adjacency. Of course, there are many other relations that fulfill those two properties, but let's work with these. So let K be 4 or 8, meaning 4 adjacency or 8 adjacency. Let's take 2 points on the digital plane, and let's take a subset on that digital plane. We will define the K path from point to another point as a sequence of consecutive K adjacent points, where the first one is P and the last one is Q. It's very natural, right? The points will be called to be K connected in the subset S if there exists a K path that we previously defined in the set S from those 2 points, from P to Q, okay? The set itself will be said to be K connected, so 4 connected or 8 connected, if any 2 points of the set are K connected in that set. And of course, we can also define then K components of the set as the maximal K connected subsets of that set. So you can see here that we have defined connectedness as well as some other notions by just using the adjacency. We haven't defined any topological space, so we are not dealing with topology yet, but still we have the connectedness. As an example here, so the same set, let's say S is the set which has these dark or black points, and we are in Z square. Suppose that this is infinite, even though you can take as a subset this as well, as the universal set. Then if you see this in 4 connectedness, you'll have 3 components, in fact, here. So these 2 points form a component, 4 components, right? This point alone is a component, and the others here are also another component. But if you see as an 8 connected set, this is only 1 component. This is all connected in 8 connectedness. Okay, I suppose you should have heard about Jordan curve theorem. Let's remind of that. So if you have a simple closed curve, meaning a curve which is closed and there is no intersection with itself, right? Then that simple closed curve splits in R2, of course, in the plane. It splits the plane, it separates the plane into 2 components, the inner part and the outer part of the curve. And let's try to take a similar theorem, but when we are working on a digital plane instead of real plane, R squared. Before that, we first need to define the notion similar to that simple closed curve in the case of digital plane. So let's suppose that K is one of those 4 or 8 for the adjacencies. And let's have a subset S of the digital plane. Then we say that S is a closed K curve, so closed 4 or closed 8 curve, if it is K connected and every point in S has exactly 2 K adjacent points again in S. So this will somehow give us a similar notion to closed simple curve in R2. So as an example, you can see this one. This is a closed simple, in this case, it's a 4 curve, closed 4 curve. So you can see any point here is adjacent to only or exactly 2 other points, and it is connected, 4 connected. And if you want here to state the Jordan curve theorem for this case, what would you get if you want to count the connected components to the digital plane minus the curve? You'll get not 2 of them, but 3 of them. So this is a connected component, a singleton, this one as well, and then you have the rest. So somehow it's not natural, right? So instead of having only 2 connected components, the inner part and the outer part, here you have 3 components. And there are similar cases like this. You can take other examples as well. Or also if you use 8 connectedness, you'll get something similar again. So this was a problem that Rosenfeld solved in the following way. He used 4 adjacency for the black points and 8 adjacency for the rest, or vice versa. You can use 8 adjacency for the black points for the curve and 4 adjacency for the rest of the points. And then you have the following theorem. So let K be one of the numbers 4 or 8, and K bar be the opposite. If K is 8, K bar 4, and vice versa. Then a closed K curve S in the digital plane splits the digital plane into exactly 2 K bar components, the inner part and the outer part of the curve. So on this case, this holds. So you can see the same here now. So if you see this as a 4 connected closed curve, then here you have an 8 connected component, the inner part, and an 8 connected another component, the outer part. So now the Jordan curve theorem holds. Except of connectedness that could be defined using adjacency, we can also define some other topological notions without having a topology here, such as boundary and interior set. So let's K and K bar are, as we stated before, let's S be a subset of the digital plane. And an element of the set S, we will usually call them black points, and those of out of that set we will call as white points, as we had the pictures shown previously. And we will define the adjacency of black points to have K adjacency and the adjacency of between two white points, or a white and a black point, to have K bar adjacency. On that case, we can define the following. So a black point will be called the boundary point of the set if it is adjacent to one or more white points. And the set of all boundary points, of course, will be called the boundary of that set. And similarly, a black point will be called an interior point of the set if it's not adjacent to any white point. And the union of interior points of the set is interior of the set. So as an example here, you can see that only these 2 points are interior points because they have no white adjacency or adjacency with white points. The rest, any point that you take, will be adjacent to a white point. For example, this one, even though at four adjacency, it doesn't have an adjacent point, a white point. We should see these on 8 adjacency, in fact, and it has a white adjacent point. Okay. Now we move on to the Kalimsky topology. First, we introduce the notion of topological digital topology. So let X be some topological space. And for 2 points, we will say that they are adjacent if the set consisting of only those 2 points will be connected in the space. So we have defined adjacency using topological space, so in a topological space. And if we have a digital space, we will call that topological if there will be, or if we can find the topology on the set of points that will generate the adjacency relation. So while we have a digital space, we have a set of points and we have the adjacency relation, and it will be called topological digital space if the topology there generates the adjacency in what we stated previously, in that sense. It is shown that the digital plane with 8 adjacency is not topological. So you cannot find, or you cannot define a topology in Z squares so that it will be, it will generate the 8 adjacency. However, you can do so with the 4 adjacency. So the digital plane with a 4 adjacency is a topological digital topology, or a topological digital plane, digital space. So the set of topological digital spaces is not empty. However, not all digital spaces are topological. And yeah, we saw that we can use these 4 and 8 adjacencies. We can define some topological notions, but we saw that 8 adjacency isn't a topological digital space. On the other side, even though 4 adjacency was a topological digital space, the Jordan curve theorem didn't hold in 4 adjacency. We needed the help of 8 adjacency to make sense of the Jordan curve theorem. So the question that might arise is, can we find a topological digital space which will be on which the Jordan curve theorem will hold, compatible to that? So, and the answer is affirmative. For that, we need to introduce this Kalimsky topology. For introducing the Kalimsky topology in the digital plane, we first define the Kalimsky topology in the set of integers. which can be generated by the following subbase. So you will take 3-element sets of integers, consecutive integers, starting with an odd integer. And you have something like this on that case. So the topology here will be, I've circled here the open sets on this topology. So if this is an odd integer, you have odd, even, odd. So 3, 4, 5, 5, 6, 7, and so on. So of course, these will be open sets since they are in the subbase, but their intersection also is an open set. So this singleton is an open set. However, this one is not. This will be a closed since the complement of this point will be an open set. So odd points will be called open points because they will be open as singletons, and even points will be called as closed points. We can notice also that we can define another topology, the set of integers, taking first an even number, and that 1 plus 1 and that 1 plus 2. And we can see that the topology defined like this will be homeomorphic to the previous topology that we defined. So it's not important if you take the subbase starting with subsets with an even number or with an odd number. The topology will be equivalent. Okay, this Kalimsky topology in the set of integers will have some special properties. It's not cost, it's cuts to distinguish. So connected order topological space is a connected topological space such that whenever you take 3 points of the space, if you delete one of them, the rest will then be separated into 2 components. So if this happens to a connected topological space, then that topological space is called to be connected order topological space. And any connected order topological space induces a total order by using the properties given as definitions here. Also, we have the Alexandrov space. I suppose most of you or all of you have heard. It's very it's a known notion, or sometimes it's called the smallest neighborhood space or minimal neighborhood space. And here we have a particular postulate, how I can say, except of the arbitrary union of open sets should be open. Here also the intersection, the arbitrary intersection of open sets must be open. And in the Alexandrov space, each point has a unique smallest open neighborhood. And yeah, our Kalimsky topology is both connected order topological space and Alexandrov space. And now we can introduce the Kalimsky plane as a product of 2 Kalimsky lines, to Z times Z, where Z is equipped with the Kalimsky topology. Here we can have a product of 2 open points on this case, a product of 2 closed points, and a product of open and closed point. The product of 2 open points will be called an open point again. The product of 2 closed points will be called a closed point again. And when you have a product of an open and a closed point, we will call that a mixed point. The open points and the closed points in the Kalimsky plane will also be called both, so together, as pure points. So you have pure points and mixed points, with other words. And we can also define the adjacency in the Kalimsky plane. Well, it's the same as the definition when you have topological space, how you define the adjacency between 2 points. Since the Kalimsky plane will be a topological space as a product of 2 topological spaces. Here we have a picture of how those open, closed, and mixed point will be distributed into the Kalimsky plane. So these points will be open points, the white ones. The black ones will be closed points, and then you have those mixed points. And we can show also how the adjacency would be here. So you see that for the pure points, you'll have the so-called 8 adjacency that we have mentioned before. But with the mixed points, we have the 4 adjacency. So we have this kind of adjacency. And of course, we see this now as a digital space as well, since we have the relation of adjacency. Now we want to state the digital Jordan curve theorem in the Kalimsky topology. For that, we will need to define the closed simple curve with respect to this space. For that, first we define the Kalimsky interval. So a Kalimsky interval is an interval, closed interval AB, intersection the set of integers, of course equipped with a topology induced by the Kalimsky topology on the set of integers. Now we can define a Kalimsky Jordan curve in any topological space if that subset of the space will consist of at least 4 points, and for which we will have the following property. For any point of that set, the set without the point should be homeomorphic to the Kalimsky interval. So somehow if you take the simple closed curve and you remove a point, then you get the interval, something like that here as well. And then we can state the digital Jordan curve theorem here on this case. So any Kalimsky Jordan curve, J in the Kalimsky plane, Z square, will split the plane, the digital plane, into exactly 2 connectivity components. So here we had the arbitrary topological space. Here we take the digital plane, of course, for our case. There are also some other adjacencies as 3 adjacency. We won't dig deeper into these. We will just present them. So adjacencies in non-orthogonal grids as 3 adjacency. So any point has only 3 adjacent other points. 6 adjacency, any point has 6 adjacent other points. We can also define adjacency in a space, 3-dimensional space. We have here 6 adjacency, 18 adjacency, and 26 adjacency. And now we continue to possible application to board games. So this would be the most important part here. My thoughts are that we can use this in studying and modifying territorial board games. I'm not so familiar with the game theory. That's why I took only these two games, the Go game and the Conway's Game of Life, as two games where we might apply digital topology. So let's begin with the Go game. I won't mention the rules of the Go game, supposing that everyone is familiar with the game. So we use, in the Go game, we use for adjacency for the stones and for the empty files as well. So I give another, I don't know if anyone else before me have thought of this. Maybe surely they have. It's not some breakthrough idea, but however, I'm mentioning here. So instead of 4 adjacency, we can use 8 adjacency, okay? And of course, it will make harder to catch opponents' stones on that case, because you don't need to circle them only with 4 stones, but you need at least 8 stones to circle only one opponent stone. But on that case, we may get rid of some situations as the co-situation, okay? So the co-situation is if we are in a situation like this, if the white plays next, he puts a white stone here and catches the black one, then the black may go again, put the black stone here and catches the white one, and it's kind of a loop here. And if we have an 8 adjacency, we don't have these kind of situations. At least we don't have this situation. I'm not sure about other co-situations. I haven't digged more into these situations. Maybe there might be some other, I'm not sure for that. Another version of the game would be when we use the 4 adjacency for the set of stones and empty and 8 adjacency for the empty files. And here, what I thought of would be interesting is, instead of counting the surrounded files, the number of surrounded of empty files, we can only count the components of the surrounded files. So this would be totally new game on that case. So the idea here would be to have as many empty files surround, but as many connected components of empty files surrounded. And it will make sense because we are using 4 adjacency for stones and 8 adjacency for files, and the Jordan curve theorem would hold in this case, so that it will make sense counting the empty file components. It's just an idea. Another interesting modification of the Go game would be the Kalimsky Go game. So here we won't have the 4 adjacency, traditional 4 adjacency. Instead, we will have the adjacency which is generated by the Kalimsky topology. So something like this. Then we will have on the file some points which will be stronger than some other points. For example, if you take this point here, it will be a weak point because you can easily collect this point by just putting 4 stones of the different color. But to capture this one, you need 8 stones. That's why this file is stronger than this one. So this would be interesting version of the Go game. Of course, we won't have the 5 times 5 table. I just made it easy for myself to draw a 5 times 5 table. We may again use the 19 times 19, some other versions. We can also have the hexagonal Go game like this, where we will use the 3 adjacency, and the triangular Go game, where we can use the 6 adjacency. Okay, again, here the dimensions of the board might be different from the one that I've written here, but the idea would be the same. And I've also mentioned here the Conway's game of life, how we can apply digital topology to modify this game. I don't know if I should state the rules of the game. So the game here, would be played by only one person. It's just stating the rules and having some initial states for the cells. Okay, let me continue. So the idea is that we have a space of cells. So if you are in a R2, you have the squares as cells. And every cell interacts with its 8 adjacent neighbors. And at each step of time, there will be some transitions, which will follow the following rules. So any live cell, the state of a cell can be live or dead. And any live cell with fewer than 2 live neighbors will die as of underpopulation. Any live cell with 2 or 3 live neighbors will continue to live. And any live cell with more than 3 live neighbors will die as of overpopulation. And a dead cell might be alive if it has exactly 3 live neighbors as of reproduction. Famous Conway's game of life is the Gosper glider gun. So for each period of time, it generates some live cells over here, except these here. It's just to have a clue what do we mean by Conway's game of life. And I suggest to have some other version of Conway's game of life. Maybe, I'm sure some suggestions have been before me that I can mention here. So I mentioned the 4 adjacency of the cells. Again, then we should modify the rules on this case, of course. The 3 adjacency, where we will have a hexagonal grid on that case. 6 adjacency version, where we will have a triangular grid. And in fact, that would be it. So next are the bibliography. So thank you. Hope I'm on time.
More than on time. Thank you, Emin, for the presentation. And maybe you can close the presentation window, and we can move into discussion. So if anyone has a question or suggestion or just wants to say, just raise your hand virtually, and I will try to moderate. The first question comes from George Nuncil.
Hi. Can you please show the slide with the references again, please?
slide with what?
References.
References? Okay.
Yeah.
Just a moment.
You'll need to share your screen again. Thank you.
Yeah. I'll share the file also with you. You can have the file as well.
That would be
Or I'll
awesome.
give to Tiago or Lisa, and they might share to the
Yes.
all people.
Okay, thank you very much.
Are there
welcome.
any more questions?
I
Anyone
think
else?
well, I'm taking the opportunity to say something. I really enjoyed the talk. I think that's lots of food for thought here. I think it's a great thing to pursue this way of looking at the board. I think it's fantastic. I think we will get nice results if we dig into this material. I found it very interesting. Thank you very much. Thank you.
Nice to hear it.
Thank you.
Yeah.
I'm
In that
motivated to work on this.
in that regard, I would also have some comments. I mean, other than the application to cellular automata on other dimensions or other point sets. I think the more than the variation or the invention of material, it would be interesting to actually look at the game of Go or in the case of the cellular automata of Conway's Game of Life, to look how the different topologies actually affect the game, or how they can actually give some additional information on it, like which closed set or closed boundary is those kind of sort of properties. And yeah, so maybe if you have any comments on that, on the analysis of games using
I said I'm not so into the game theory, therefore I don't have any idea how we would use digital topology to analyze the games already existing. Therefore, as you could see from the slides, I just gave some insights how we can modify some rules to get some new games similar to those that we know. But I'm sure there should be ways how you can use digital topology as a tool to study the already known games. There should be.
Lisa has a comment as well.
Yeah, more a question than a comment. Have you tried to play this game with the change of properties with the agency? I mean, just like the first few moves of the game, if you change the agency of the...
I haven't.
Okay.
That would be interesting to try to play first and then study what happens. Yeah, I haven't. To be honest, I haven't even played the standard game. I know the rules of the Go game, but I haven't played a Go game yet.
Okay.
But yeah, we should try for playing the new versions of the game and see if they are interesting and move on. Yeah.
Because it's something that came from previous discussion that we had before. It was the notion of playability of a game, and so at some point I think there's some connection with the fact that the game changed a lot or not, and how you behave on the game.
You're right. You're right.
Change the properties.
We should first try to play it and then move on if it's playable. Yeah. I agree.
All right. if there are no more questions, we thank the speaker one more time. Thank you, Emin.
Thank you for the opportunity.
And we look forward to continue, to continue speaking about these. Our next session is scheduled to be in a month from now. Lisa, do you have the dates on hand?
It's the 13th of May. It's a Monday.
So it's the Monday on the 13th of May, and we are trying to schedule these to be on the second Monday of every month, always around 3:30 Portuguese time, which is not the official time we're using. We're using 4:30 Central European time. That's Paris, Berlin, 4:30. And for the rest of the world, well, you'll have to adjust to your time zones. Thank you very much, Emin, and thank you very much, everyone else who turned up.
Thank you to all of you.
Thank you.
Bye-bye.
Bye.